of problems which could act for us as research problems. Now, I say this because unlike some of the recognized research institutes, a typical academic institute may or may not have the resources, the infrastructure that would be required to take up topics of current interest and, which requires a lot of investment. But are there problems which a typical academic institute, a college or university can take up? Okay, so that is something which I would like to kind of also brief, and then of course we get on to saying how typically research papers could be written by younger students, could be undergraduate students, or could be postgraduate students, and or of course graduate students, essentially PhD students and so on. So that is the kind of thing that I want to spend some time with you. So let me, without more delay, let me start sharing my screen. I hope the screen is visible. Can someone confirm that if the screen is visible? Dr. Sudhir? Visible. And also, are you able to see the slides changing?
Yes, sir. Yes, sir. Yeah.
Okay. Okay, fine. So this is the title that Dr. Sudhir asked me to speak on. And so this is Art of Writing an Effective IEEE Research Paper. But the last two words are, of course, important. Every good paper also requires a good research. So that is what I was trying to kind of give a brief before that. Let me start defining a little bit on the words that probably we'll use for the rest of the presentation. When I really meant academics, which is typically what is kind of shown here in terms of a classroom kind of environment that many of us know and many of us teach. So the work that happens, the academic work that happens often relates to the kind of work done in, I say even schools, but well, we may not have someone on the call, but colleges and university. And what it actually involves is studying, or even more importantly, reasoning of various the scientific principles, all right, rather than actually spending so much of time in building instrumentation or experiments or technology and so on. CRB, when we teach our students, we teach them, we empower them, we kind of encourage them to reason out certain principles. It could be mathematics, it could be physics, it could be engineering and so on. Often we say, how do we go about arguing or reasoning out or studying certain things from known principles, which of course we learned, let us say, in the previous year or previous class and so on and so forth. So please remember, academics always talks about reasoning, and that is how we want to make students understand the basic concepts of either science or mathematics or engineering, right? And there's not so much of, as I said, building things with your hands. Of course, our students go to the labs, the teaching labs, and do certain experiments. Sometimes they try to test out certain concepts which they learned in the classroom, or sometimes maybe we demonstrate to them how what we taught in the college or the classroom becomes something which the students can see and learn, but not so much in building things by ourselves, right? Whereas the research that I was talking about, one that is shown on the right, where it involves a very, very gigantic, sometimes experiments that requires to set up a lot of money, a lot of people. This is what I say that the typical research institutes, they also do something what is called systematically studying something. And what is the purpose? Well, the motivation is to discover some new facts about it. So, for example, I would like to, if I'm working on a physics area, I would like to kind of study a concept of physics so that I want to discover something new fact, which obviously did not exist. So the research material that goes to write into your paper actually gets generated within the framework of, let us say, the lab or the experiment that one sets up. And as I said, this could be a big business. It could be involving billions of dollars. Sometimes nowadays, modern physics experiments are extremely complicated and very big. It involves lots and lots of people and money, as I said. Of course, time as well. Sometimes some of these experiments, for example, the one that you saw here on the right, took almost 25 to 30 years from the word go till the time when the data started coming up from experiment. You can imagine this is not possible to have such kind of research setups in a typical academic institution. The other component that we are all familiar with, again, the picture that is shown on the right, it's probably an aircraft manufacturing industry. Is actually work or process that gets involved because you actually collect certain raw materials, make them into products so that you can roll out of the factories. And main intention of industry, of course, is to do business and make money and so on. And some of the industries like software, we also talk about so-called consultancies and services and so on. We don't make tangible products, but we offer our consultancies and services to develop certain products. It could be software, it could be giving a consultancy and so on and so forth, right? But here too, industry too uses certain materials, certain resources that are specific to industry. Okay, what I really wanted to say here is that when you undertake research, doesn't matter in which part you're talking about, academic or research institute or an industry, you kind of generate certain impact by doing a frontline research, which of course attracts quite often higher grants because it resulted into useful academic activity. And then, that will encourage you to take even more research and publish some of your findings, increase the impact of an individual or an university or a college and so on. And then, of course, therefore, your college or university will get even a higher ranking and attracts higher grant incomes and so on. This is a very positive kind of an environment and ecosystem that happens when academic institutions besides teaching, which is the bread and butter of an academic institution, it also helps to kind of generate certain very healthy ecosystem that in turn helps not only the students and faculties, but also the institution at large. So here I really wanted to end this slide by saying that research can equally excel, not just in the earmarked research institutes, but also in the academic as well as industrial establishments. Whereas in the academics, the main resource are the students of all classes. It could be undergraduates or graduates, as I said, or the PGs, or in the industries where the big resource is, for example, the equipment. I mean, industries have huge equipment that becomes a part and parcel of producing, industrial products. So therefore, that is also something which is required in some way to set up a kind of research ecosystem or infrastructure. So the resources are different. One is in students, and other one is in equipment. But my claim is that you can also do a reasonably good research at these two organizations, namely academics as well as the industry as such. Okay. Now, of course, this is a slightly philosophical question, and why not research in some way? I mean, I take this very slightly funny, but slightly also realistic in some way. Example, also which connects up to all our childhood, right? I mean, when we are born, we always ask questions, and remember, the main kind of requirement of a science or scientist or a research or an experiment is actually ask the right questions, right? And when we are in school, many times we might all remember either we like a subject very much, and then we kind of make a career out of the subject, or sometimes maybe somehow we dislike a certain subject, and then we decide, no, this is not my cup of tea, and I don't want to kind of do research or anything to do with this particular subject. And more often than not, with all due respect to the teachers on the call today, quite often it happens, it all goes to some of the outstanding professors or teachers in our school who develop and inculcate such interest in us. And maybe some of us are very good in a subject, but maybe we lack a little bit of our maybe teaching skills, and maybe some subjects look very difficult for the students, which discourage them sometimes to go ahead and do research, or for that matter, pursue that in further way. This is what it happens. So therefore, quite often it happens either the parents or teachers decide to kind of polarize themselves into doing things which is more safe to be a kind of employee working there, rather than getting on to do things like become a scientist or do research and so on. And quite often we influence our children, and we kind of sometimes prevent them to take call on what he or she wants to do. And to kind of drive my points, I bring up on the screen even the case of Dr. Homi Bhabha, who is our founding director, of course, one of the topmost scientists of the world. Even he had to kind of plead with his father because his father wanted him to become a mechanical engineer. But Homi, of course, we all know that he loved science so much. So he kind of argues with his father. You say, for each man can do best and excel in only that thing of which he is passionately fond of, in which he believes, as I do, that he has the ability to do it, that he's in fact born or destined to do it. He is very strong that he actually wanted to do science. And he in fact says, I seriously say that business or job or as an engineer is not, thing for me. It's totally foreign to my nature and so on and so forth. And he says, physics is my line. And, he kind of argues, I therefore earnestly implore you to kind of let me do physics and so on. I mean, I'm just kind of sharing a certain anecdote to just drive my point, as I said. So the rest was history. His father still insisted that he must do mechanical engineering, and then he did it. And then his father agreed that now you can go ahead and do what you like. And of course, Homi Bhabha became the world's famous scientist doing research, or did lots of things in high energy physics, and also built great institutions like TIFR, BRC, and a lot more of the organizations. Okay, that's so much about the how the research or no research really affects when we are still very young. But I want to really catch this aspect even at a level of undergraduate research. Why I say this and why I show this slide in some way is in the IEEE, the groups or the sections and so on, whatever, our main say is the student branches. The student branches typically of engineering, or sometimes the other student branches, where most of our catchment area lies with. So we have to really work on something which, let us say, maximize the reach and the benefit of the student branches and the students therein, which are largely undergraduate students. Now, the question to ask ourselves is, since our resource here, just like what I told you some time ago, or the undergraduate research, is there something useful, something impactful that can be done in terms of research using undergraduate students? We know how to do research when they're big scientists with gray hair and long, beard, and those people are what we call scientists. But can that be also done by in the ecosystem of academic institutions involving students? So my claim is that it can be done, and this is a kind of research we kind of talk about, which is exploring very, very tiny but a specific area, and which is kind of still being kind of studied or understood by an undergraduate student, and still in some sense it can result into a original contribution, because without your original contribution you can't write paper. You can't just simply copy from here and there and write a paper. But surprisingly, it is fairly a recent concept which only happened in 19th and 20th centuries. And it actually all started in 1810 at University of Berlin, but it became very popular. The undergraduate research has become very popular when MIT took up what they call Europe, which is Undergraduate Research Opportunities Program in 1969. And then the whole world caught up, and today the undergraduate research in one form or the other has become quite common in most of the establishment. And it is, I must say, it caught up very well in Indian scenarios also for the last about 10 to 15 years. And it is inspired, or in some sense, came up on the center stage just because there are some very proactive, I would say, initiatives by governments which also kind of encourage students not only to kind of work on creative concepts, but also empowering them to look at opportunities other than doing, what we all call very safe jobs, namely entrepreneurship and, startups, and picking up things from there, and, and basically kind of try to do something very creative, something a research bent of mind, and expand their scope into doing something very, very, very useful. And quite often, they become a big, very successful entrepreneur. So this is a good thing that kind of happened. But while the students are in the colleges, typically undergraduate colleges, they kind of understand what the research process is. It's very difficult for a school child to kind of understand a concept of how scientists work, and understand that in order to say something, in order to say an hypothesis, it actually requires certain evidence. When they go to teaching labs, this is what they will be doing. They go with the concept from a classroom and actually set up an experiment, or at least do an experiment which is already set up, and prove, take readings to support the evidence. And they understand that, look, the theory that I learned in the classroom requires a practice in my lab to be able to integrate these two things. And they kind of, now you can see that how from the basic concepts of chapter 1 to the last chapter, how the knowledge gets constructed. And, how do you, for example, set up experiments in the lab? How do you analyze the data that I took readings in the lab, make a graph, and interpret this data, the results, and so on. And the confidence that the students gain, the self-confidence, able to work independently. And of course, more often than not, when you set up an experiment, when you do even readings in the lab, you find that the readings do not match, and then there are obstacles. Maybe the equipment doesn't work, and so on. And then you repeat. Quite often, we all face this problem in the when the student is setting up an experiment, the external is standing next to him or her, and then the equipment stops working, the readings do not make sense, and so on. And this is how the real life research really happens. And that brings them to kind of understand the importance of science, technology, engineering, and mathematics. And most important of all that is developing such skills in critical thinking, communication, more often make them not just only experts in physics, chemistry, biology, whatever, or also make them leaders where they will be able to kind of go out and lead multiple professions in graduation. So, of course, as I said, the university or institution itself will benefit from the publications or patents that come out of such a research when it is properly organized in. And of course, the colleges improve their branding, ratings, rankings, funding. Nowadays one hears all these quite often to make the college very popular. So, but before I get on to kind of even talk about certain possible topics, I just want to take a couple of minutes to say how important is the role of management in setting up such an ambience here, because you're required to kind of do very conducive ambience on the campus. Nowadays, of course, as I said a while ago, many of the colleges, they set up innovation cells, incubators, and so on and so forth. And they must encourage both student-generated small projects as well as the mentor-generated research topics, which are essentially faculties. And you set up and efficiently maintain the research laboratories. I don't mean the teaching laboratories, but the research laboratories. It's very expensive to set up those labs. So you can't have research laboratories encompassing all those areas but maybe you have to choose a few topics in which your own faculties are motivated to do. Maybe you find a few faculty members, they already have proven a point by publishing good results, maybe interested to set up something new. So you pick up a few selected topics, and so that you give the financial assistance to the students and faculties to attend conferences or even benefit from some of the exposure, both international and national. Quite often, since we are now today talking on the flagship of an IEEE event, so it's also important that institutions actually fund professional memberships once again to the faculties, because quite often that is very proactive step which facilitates expert interactions, the distinguished lectures programs coming to on the campus and inspiring both students and faculties. I think this kind of a proactive role by management goes in a big way as an investment. Of course, it all costs money, but at the end of the day, I'm sure the tangible benefits are something for everybody to kind of benefit. Now, since we kind of talk the kind of research ambience, obviously, depending on which part of the sphere that you are expert in, whether you do a reasoned investigation of certain basic, phenomena which take you to the, let us say, the physicist or chemist, mathematician, and so on, which are also, of course, part of our first year graduate programs, or a person who works in technology schools, picking up the scientific principle and trying to kind of convert that into areas which will, of course, benefit ultimately the mankind, but at the same time converting the basic science principles into something that is useful concept, and picking up that concept, optimizing the resources, could be could be power, could be cost, could be the size of the device, weight of the device, and so on and so forth. Can I build a product out of that and optimize the resource and ultimately making it a product that can be afforded, where the engineering community comes into the play. And as I also mentioned while I was talking to the science faculty, the mathematicians out of you also can really pitch in. And I will tell you a couple of such examples how this becomes a major research activity that can be practiced on the campus. So whether you belong to a technology person, an engineering person, a mathematician, or let us say the basic science faculty, science, biology, physics, mathematics, or whatever, I'm sure there are these opportunities, a window of opportunities, I would say, for able to kind of do certain things which can generate original research output. So I'll give you a few examples later, maybe in my in the presentation. So one thing that comes often to us when we talk about research and topic, what is the topic that I must choose? Because whichever topic I kind of think that I should do research on, I always find nowadays on Google that this already a big research is done, and there has been a lot of new work has already gone, published thousands of papers. So that means maybe the whole thing is kind of already done. Today, I mean, just before I came online, I was reading in a Facebook on somebody's post. It was talking about Max Planck, and it said that it's apparently Max Planck's guide or teacher told that, don't waste your time on doing research, in science or physics, because everything is already done. There's nothing left for you. Okay. But luckily, Max Planck did not hear or listen to, or maybe did not have much of faith on his teacher, but then he went about and, he was, whatever all we read today in quantum mechanics, the entire modern physics, he is considered a father. Of course, he is also Nobel laureate. So there is nothing like to say everything is kind of done and there is nothing left here. But nevertheless, it makes sense to kind of ponder a little bit what is the best topic that you would like to choose as a student or as a faculty. And, many times we know certain topics, we don't know certain topics. So we should kind of identify these are the ones that I know that I would like to work on. And not just knowing, but I really love to work like the way I shown Homi Baba's example. But that's not enough. Quite often, the world wants to kind of like you to kind of do research on some of the front ranking topics, not some topics which do not have much visibility. So what it makes sense is maybe like a Venn diagram. So maybe the area common to all this, is I think what probably the things that you must choose. And on the left, since again it is an IEEE meeting, I try to kind of tell you on an IEEE Explore, which is online repository of IEEE conferences and journal publications. If somebody asks you, let us say, what are the technologies that fuel fourth industrial revolution? It's called Industry 4.0. And you can actually see literally, almost hundreds of thousands of documents that exist. IEEE Explore is like, several tens of million documents that are stored. And you can really see that depending on what topic you are interested in or talking, and those many documents are there. Now, if you're a person who looks at and say, oh, look, there are 100,000 documents, papers, and so on IoT. So IoT must be one of the very hot topic today. Big data may be one of the hot topic. Autonomous robots could be one of the hot topics and so on. Maybe those are the topics which will come close to your heart. Maybe you'll love them. Go ahead and actually do work in such kind of things, right? But fine. I mean, that is one way of looking at. But here I give you a little bit more practical way of choosing a topic, right? For example, we all know, a typical quadrant here, a graph, in which I can kind of make you to look at 4 segments of, problem space, if you want to call that. There are hard problems. There are easy problems. There are problems which will give you a little small gain in knowledge. It won't be a Nobel Prize winning kind of a discovery, or some of them give you a big gain, maybe an outstanding research output is going to come, right? Now, if I just ask you, what are the kind of problems you like, you will tell me that I would like to solve, I would like to take up problems which are very easy, but at the same time, give me a large gain of knowledge. That is what is our bullseye, right? Of course, there is no surprises on that. But you also know that normally it doesn't happen that way. Hard problems take, large gain of problems take hard, problems, and then you have to put big efforts. So how do I do it? I actually go to the right plot and keep looking at and say, look, there's no point in spending a lot of hard work and then say only small gain I get. I don't want this particular one. Okay, if I'm a student or very young faculty or postdoc, I would like to kind of pick up those topics which are relatively easy. I know that they are going to give me so-called low-hanging fruits, which are give me a little bit, research output. May not be earth-shattering output, but it's okay. It will give me something where I can publish a paper. Maybe I publish a paper in the IEEE journals or maybe a conference. Okay, but if I'm a little bit a senior faculty or maybe postdoc or somebody, maybe I can then try to attempt problems which are on the higher quadrants and so on, right? Of course, these kind of hard problems which will give large gain, fair enough, but I better leave them to dedicated research institutes because it requires big infrastructure. So maybe to some extent, before you latch on doing some problem in order to write a good paper, better to introspect yourself and see what is that, I can gulp, what is that I can actually easily achieve, because I have to spend 70% of my time in trying to teach students, or students 70% or 80% of their time, you have to really learn to, understand the subject and write your exams and pass successfully. So therefore, you're not left with your 24 hours to do research. So you pick up that little problem which will help you to kind of do things. No matter what problem you chose, which research problem you picked up successfully, you should start by saying, okay, what do I want to kind of do research on? What are my research objectives? I picked up my topic. Okay. Then luckily for us today, we have internet, we have Google. So I can actually go back and say, okay, this is my topic. I want to do something on IoT. I want to do something on sensors. I want to do something on maybe neural networks. I want to do something on AI, ML, DL, whatever, right? Now I go back and look at what kind of research is out there right now already done by people. And then that what allows me to delimit. What do you mean by delimit? Delimit means, okay, I know I want to do this project, but I want to then draw a line around and say, this is my specific research problem. And in there, I will actually put forward a theory, a hypothesis. And then if I want to prove this hypothesis, what are those variables? What are those research variables that I must measure? How should I design an experiment by myself? How do I kind of write some software so that the data that get collected can be analyzed? And then I'll go ahead and do the data analysis. And, the plan for analysis. And then I collect data processing, analysis, and interpret, and conclusions and recommendations, etc. I'm very happy if I can come to this point, because I started with a hypothesis and then I came to conclusions. Then here is the point that I can ask these questions when I analyze the result. Do you think the hypothesis is true, or do you think the hypothesis is false? That will kind of allow me to kind of move forward and say, and then if unfortunately if the hypothesis is false, I might want to kind of change the experiment and pick up another kind of the data and the goods. And sometimes it is an iterative process. This is what I said. The students all learn that it's not always that the results come in the first attempt and so on. If I am able to come up to this is the time when I can think of sharing my research output with someone outside. And the only way to do that is by writing a research report, a research paper, and that is the starting of able to kind of start sharing. Well, when I came out of an experiment and looks, I'm quite excited today because I seems to have discovered something. Now, the question that I want to ask is, should I go ahead and publish as a paper, or should I actually, let us say, apply for a patent, or should I keep it to myself? Don't tell anybody, because this seems to be a big mine of opportunity, because it's a gold mine, because this is something which nobody knows and I can make a big money out of it, right? Now, the question to ask is yourself, is the amount that I'm going to kind of spend on publishing, patent, right? Is it worth, am I going to get something out of it or not? This is the question you have to ask. And this is important because you spend certain amount of money and only a few % of those ideas which you kind of, file a patent actually gives you any revenue. So quite often, if that is not the case, you go ahead and actually make a nice publication, because at least it will add to your CV. And tomorrow, probably you will be a person who will be well recognized for the research in that field. Okay, as I said, but just for completion's sake, I also put here trade secret. If you think this is a secret which you don't want to even publish, because you can keep it to yourself and then make a big money out of it, just like all the fast food guys or maybe soft drink fellows actually make, or some of the medical drug manufacturers are also make money. You can keep it to yourself. So these are the three main ideas, but let us focus only on the publication of papers, because that is where we want to spend today's time. And when you talk about when you decided that you want to publish, okay, and it is important, just because if you don't publish, then that is the only way that you can inform others, right, that you have done some work, right? Otherwise, what happens is, if you have done work and if you don't publish, the guy who actually publishes later, who does and publishes paper later, the credit goes to him or her, right? And if also some of our co-faculty members think that if we don't publish it, that means maybe we have not done good work, okay? And it is actually important as the first step, at least start writing down into a report, because then maybe when you write down, you yourself will feel happy that there is something worth publishing and so on. So that is how, this particular saying that came, like, publish or perish, it came, right? And this cartoon on the right side says, this person did not publish, so he perished and so on. It's quite important. It's quite important to, write down, because sometimes while writing down and publishing, it will open up completely new problems, not only for us to continue, and also maybe our students and other faculties. So it's quite important in that sense of opportunity. Okay, so let me move about telling you a few typical problems of what an undergraduate can do. Some time ago, there are a couple of second-year students came from a college and they said, sir, we want to do something build in your lab. I said, look, we don't work in all those fancy AI, ML, DL, and those kind of areas. We work on so-called high energy physics, which requires certain instrumentation, certain detectors to build. He said, sir, we want to build some detectors like that, and we want to study the cosmic rays and so on, which is quite alien to second year, third year students. But I was very happy to show, that's why I'm showing you this picture. They actually built one such equipment involving the detectors, which can detect so-called the sensors, which can sense the cosmic rays in the atmosphere. And they end up actually using one of the facility of KIFR at Hyderabad, and they actually flown that entire, the payload up there by almost 30 kilometers using this balloon. And they picked up such a nice data, they could publish it in an international conference. Of course, this particular event was so successful that, the entire country looked up and watched that just second year, third year engineering students can actually build such an experiment. And of course, they won a lot of awards and so on and so forth. So it is quite possible if the undergraduate students are motivated to be able to kind of do such experiments. But for the faculties at large and also the students, depending on whether they belong to which branch of engineering, I want to give you some 2 or 3 very quick examples. Of course, we all know integrated circuits, which we use to build a lot of electronic circuits in our labs and in our research labs and other places, right? And these are the chips that we go to the market and bring them and make a printed circuit board and then write a logic equation and implement that circuit, right? These are what are called, industry standard integrated circuits, which large number of industries make them in the very cheap, the very easily affordable by students and faculties. But quite often this concept of so-called programmable logic that comes in, because these chips are not programmable. These truth tables are decided by the manufacturers. If you want to build any programmable, any logic that you want to build during the development, we normally use what we call programmable logic. Of course, there is a whole history of programmable logic which solves problems of what I told you, which is a fixed logic. And if it is programmable to me, then I can use my own concepts, my own architecture, and in the field that I'm equipping, or let us say making a product out of it, and then probably I can enhance the functionality and performance of the system, right? So one such thing, some of you I'm sure know about it, is the field programmable gate arrays, which are the top end of the programmable chips these days. And they will enable you, because you can program the product features or the functions, or sometimes even adapt to new standards, reconfiguring the hardware and so on, after the product itself is produced. Like I can use these chips, make a product out of it, install in your home, and if you give me access to this, I'll be able to kind of even upgrade, let us say, the functionality of these chips and so on. So naturally, these have become quite popular these days. And because the chips are made of programmable logic blocks into which you can fuse, let us say, Boolean logic or algebra, I can also connect those logic blocks into the neighboring logic blocks by programmable routing matrix. So it's literally saying, I can connect one part of logic block into other logic block, and even that connection could be of programmable in nature. And ultimately, all that circuitry that I have access to, programmability inside, can also be brought down to the pins, because ultimately, after all, it is connection to the pins that makes the circuit functional and useful and so on and so forth, right? Now, here I just want to give you an opportunity for the research where, since these chips are programmable, there is this concept of so-called IP, intellectual property, that came about in this hardware-based environment, where I can pick up the FPGA's fabrics, which is actually fabricated by certain companies, and then can I actually build devices like some of these examples that I've shown to improve the functionality. Maybe I optimize the power, I want to optimize the cost, or maybe reduce the time to market when somebody is building product out of it, and improve the reliability, because I have already made a code which will go and sit in these FPGAs, and that can implement many of the popular kind of building blocks, which a product designer can pick up this and go ahead and make a product out of it. And what is the advantage? The advantage is the product designer doesn't need to kind of reinvent the wheel. The entire thing is available with someone, sometimes for gratis, sometimes for free, or sometimes you have to pay some nominal IP to have the access to that. And then it will allow me to make the product much faster, much reliable, at lower cost, lower power, and reducing the time to market and so on. This is a wonderful opportunity for faculties and students on the academic campus to be able to try out and work on the IPs that can be done on a programmable chips. In fact, to allow this to happen, even many of the manufacturers set up a good ecosystem in terms of saying that, giving a reference designs and giving the IP cores, producing the development kit so that you can test out your designs, and of course, also giving you evaluation mode of the FPGA chips, and also ultimately what you call engineering design tools, right? EDA tools, like for example, in this case, if it is Intel, there is a Quartus, and similarly for Xilinx and so on and so forth. So even the manufacturers of the FPGAs realize that IP development is an important aspect that will bring value not only to the developers, but also to the company at large. Because if you can boast yourself saying there are millions of IPs over there using our chips, our hardware, obviously they will be able to sell better. So it's a kind of win-win situation for everyone. The other important aspect that I want to kind of say a little bit to the faculties out there who are from basic science or mathematics is kind of see, can I really do simulations or mathematical modeling on problems which are very difficult to solve, not very easy to solve analytically. For example, can I pick up certain parameters of my interest, and then I say I want to predict what is going to happen into this system of two variables. For example, the parameters are theta, and then I say these are x and z are my predictions. And after that, when I predict it, I will observe this data, okay, let us say of x, and then I come back and say that, okay, I have these parameters and I have predicted certain x and I observed this x. What is the difference between the observed value and the predicted value? Sometimes you can call that as a nuisance parameter, the noise parameters in some way. Okay, and now you optimize this cycle to solve problems of very, very high interest. Now, this is just a basic concept. When I give examples of such type, you will realize how such a simple paradigm of recurring process can help you writing good code and get good results. We know that, okay, simple like dots that are there in a straight line, we can fit into straight line very easily. But if you have a lot of noise around along with the straight line, the methods that I mentioned to you with a repetitive prediction and realization can solve that problems to give you a very good linear fit. And now if you go down to even higher problems where there are thousands of such tracks, they're going in a circle because there is a magnetic field and so on, or maybe there is data points which are not just simple y equal to mx plus c, but let us say higher polynomials. The methods that I described will bring out nuances into the data that I have, and which will probably bring a new research output. Some of these problems which cannot be simply solved by writing down an equation, which are what is called sometimes learning system, sometimes they're called multivariant systems. Like one of the examples is neural network, where I don't know what is expected from deterministically from a value. For example, if it is just straight line here, as I said, you can just fit it with a linear equation. But if the same straight line is fit with lot of junk, lot of noise, I will not be able to fit that properly. So what is the best method? The best method is to set up a neural network, start feeding millions of test samples, and look at how the so-called weights between the input nodes to the middle hidden layer to the output gets adjusted. And ultimately, when I want to solve a problem, I will test out once the weights are all properly done. I'll test out on maybe a subset of samples. And then when I actually feed the right sample with where there is a track as well as data, can it decipher and give me the track that I'm expecting. Of course, it requires a choosing of the right architecture of a network, the right sample, large number of sample, obviously, to be able to kind of, the architecture, because some complicated networks require much larger hidden layers, not just one layer. For example, here I'm showing a person, the entire data, if I want to feed into as an input layer, the data can come from family background, the data can come from pathological information, the data can come from many other inputs. Now, using those, if I can set up a huge network and then predict a person's health, or ultimately, for example, in the days of COVID, you can actually see what is written on the top of the slides, literally starting from embryo selection for IVF all the way to the right, where one predict death of a patient in the hospital. That is the kind of sensitivity the neural networks have reached today. Okay. Now, as I said, sometimes these problems are not something predictable. So then people also use what is called Almond Filter, where you start from a known state, a prior knowledge of what is state, and predict the next step, and both in terms of what is the probability of this happening, and as well as what is the estimate of error. And then you kind of make a measurement on that particular step and compare with the prediction. And if the error is very small, you quit and say, this is how I solved the problem. Otherwise, you go to the next and so on and so forth. Using such kind of networks, people were able to kind of analyze such a complicated pattern recognition. And that is what won Nobel Prizes for science and other fields today. Okay. People also use such kind of medical techniques to have imaging of pictures that are shown using, let us say, so-called color X-rays or other chest X-ray pictures that are kind of taken using very sophisticated medical equipment these days. But these pattern recognition, which is used to use these techniques like neural networks, have actually brought out a very high resolution pictures of what is happening at a molecular level inside the body, and predicting the diseases or any problems much earlier than what can be done by conventional ways. These techniques have been put to use extensively for the last 2 years, and I don't have to tell the reason for that. And then it has now reached to a level where one was able to kind of achieve something like 98 to 99% of sensitivity of looking at what happens in the lungs of a patient suffering from corona or other pneumonia and such diseases. And so they have really grown. So setting up a problem in space, which is not building certain hardware, but actually setting up on a computing system, solving real life problems have become very common for the last 2 or 3 years. And now you have systems which are like this, which are free out there. So open source, both in the data samples as well as the neural network, which is 120 layer network. And you take up the data samples, which are hundreds of thousands of samples. You can work on any of the diseases, standard diseases that can be deciphered using chest X-rays. And today you have such networks which outperform even the human radiologists today. And these kind of small problems taking up, and people are able to work not only in medicine, but even on the agricultural field. Today, one of the main field where these techniques are applied, or besides medicine, is agriculture, animal husbandry, and so on, where you're required to kind of monitor the health of crops spread over large areas and able to kind of predict using pattern recognition, predict certain growth phenomena or no growth phenomena, and able to kind of help assisted systems to the farmers and so on, right? So today, when you talk about systems which are not necessarily any engineering systems, it could be civil, mechanical, or any such a product, can I really convert that big systems? It could be a dam, it could be a flyover, it could be a big system. Can I bring down by mathematically bringing into a model so that I can apply standard mathematical techniques to solve such problems, and then I'll be able to kind of predict what happens for the actual civil structure. As you know, when we write down an equation, we say there is something y equal to, function of mx plus c or whatever. We say that they're dependent variables, the independent variables like x here. And then sometimes we also use certain forcing function. So, for example, when you even take simple equation like force is mass into acceleration. So it's basically the acceleration which is dependent variables on the fixed mass, which is a parameter, and the forcing function like the force that you apply. Now, if I take this a little forward, and today if I can tell you that there are, let us say I have known certain inputs here, and I would like to predict through mathematical modeling how the system behaves. I don't know what that system is, which is what you call black box. What it is important to be able to kind of predict that is by bringing into mathematical modeling and then solve those problems using what you call Monte Carlo simulations. These are simulations which require when I kind of, even if I take a simple dice which has 6 faces and keep tossing that, we know that at the end of the day, if I do sufficient number of samples, I get equal probability for all the dice, right? So therefore, the average will be, let us say 3.5. But when I start, doing first, that average may not be 3.5, it may be some wrong number. But when you go with the number of trials to be very, very large, you will be able to kind of have that kind of expected number here. So this is what is called law of large numbers. You don't know anything about the science that goes on, mathematics that goes on, but I want to kind of prove, I want to simulate certain principles and achieve very deterministic values that by using those principles. Now, I want to kind of give you just one example. If you take a square, if you take a quadrant of a circle here, and using these two concepts, if I want to understand, calculate what is the value of pi, right? Pi is 22/7, the ratio of circumference by the diameter, right? I don't have to know this equation. All I need to do it is draw this square, draw this 1/4 of a circle here, and then keep hitting this figure with the number of randomly chosen points. And I count how many points are falling here, how many points are falling here. And from the ratio of these two, I'll be able to kind of predict or calculate what is the value of pi. And you can actually see as the number of the data samples is increasing, the accuracy of pi value is also increasing. So this is what normally is done by Monte Carlo simulations. If I want to understand either in physical science or engineering, for example, if I want to, like somebody's set up a IC foundry and they are manufacturing millions of integrated circuits, I want to understand what is the tolerance of these chips, what is the spread of this specification. I don't check each of the integrated circuit, but I will be able to kind of simulate the behavior of what is, we always have this specification which is min, typical, and maximum. These values will be able to come by simulations. If I'm kind of setting up a, manufacturing, let us say, network router, I'll be able to test what is the signal that is going to have at different parts of my college. I don't take this unit and check everywhere, but I can actually do the signal strength by simulations if I have sufficient data about it. Today, they are used not just in engineering, but also used in financial technology, it's used in AI application, it's used in biology, and so on and so forth. These are problems which are very amenable for, simple with a computing system. You don't really require very, very high hardware or, the infrastructure required for what you call, for doing research and so on. Okay. I want to kind of move a little bit because I'm running short of time. Let me give you a few examples. So when you have a research output coming from any of such problems, it requires, when you have that data, how do you present in a way that makes the publication very attractive? You must remember the structure of the paper should be such that, of course, it will have a title, abstract, a basic introduction, and the main body of the paper. And of course, most importantly, the referees want to look at the discussion and of course, references and so on and so forth. This is the logical order of any paper. But what is important is these little statistics that I've shown. If 1,000 readers read your title of the paper, how many of them will read abstract? About 100 of them. How many of them read your introduction? How many of them read what is the problem definition and your idea and so on, and how many of them at the end of the day come and read the actual, the actual work of the body and discussion. That depends on whether the problem that you took or reported is something favorable or something, of interest to me or not. But everybody reads paper title, everybody reads some abstract and so on. So you have to make that paper very interesting by writing in that order, because otherwise what happens, people read title, but they will just move away because it doesn't look like, even though you have done good work, probably you did not express it properly, right? So therefore it becomes very important to follow such a kind of structure. By the way, this is the paper written by those undergraduate students. Once you kind of have your paper written, whether you are a student or a faculty, one of the important aspects is that paper should go through so-called internal review, which is actually among your collaborators who are part of the group to go through, because they are the people who know best about what is the work done and what is the work that has gone into this paper. Okay, if that it goes through the all these corrections, probably the value of the paper, the grammar, the language, the how you kind of express, especially true for the undergraduate students. Some of them also nowadays are available what they call peer review process called archives. You can actually upload onto a web portal which is free of cost. Okay, and then a lot of other people read and give suggestions, and they're very effective and very useful, therefore, to the authors, etc. So, and nowadays, every paper it has to go through peer review. Peer review are the people who are doing similar research like you and who will go through this paper. Obviously, if those people upload your paper, that means they are knowledgeable in the field and they're saying that your paper is kind of good there. Okay, so when you submit for such a peer review, usually the paper is accessed first by our editor. It's very unlikely that the editor themselves, if he or she finds it is not good, they may reject. But otherwise, it usually goes to the reviewers, and reviewers after assessment, they kind of give the the input. Either it requires some revisions, or sometimes maybe the paper is unfortunately rejected, or sometimes they may ask for reviews to be needed. But if you are very lucky, your paper will get accepted and it will be produced by publication, right? This is the general chain of things that happen. But nowadays, things are a little more complex than simple. There are the peer reviews happen, so-called in a varieties of ways. And the most common way is, basically what you call double blind, because there both the authors as well as the authors do not know who the referee is, and referee doesn't know who the authors are. That is the most objective way of doing it. But olden days, even now, some cases, single blind is there. You don't know who the author, who the referee is, but the referee knows the author names and so on. And there are very creative new ways of also doing the so-called peer reviews. So the single blind, as I told you, the authors do not know the referee, but referee knows who the authors are. In the double blind, both of them don't know each other. So this is more objective way of refereeing. In the case of open peer review, normally there is a kind of a field where the both publishers, some journals basically together, and they will be reviewers. There are many popular cases where there will be a bunch of open reviewers where the review is also published along with your article. So that really tells you that it becomes very, very transparent for people. Sometimes if the journal doesn't like your paper, they don't just reject, but they'll say, why can't you publish it in the other journal? So they transfer your manuscript to a different journal so that, it's easy for you. You don't have to start from beginning. Collaborative review is very, very recent and very important one. There, it's not just one reviewer, two reviewer. There is a collection of pool of reviewers who will review together sitting across the table, not just, one review sending directly to the editor and so on. So it's also a nice way of adding value to the review. And some of them, even after publishing, you can still get a further appraisal and revision of the work that you have done if you have discovered much better concepts than what were published and so on and so forth. So the most important thing to understand when a referee wants to look at your paper is they want to ask, if the problem is really important, what you have done, to what extent your paper solved the problem which I described on the top. And what is that so-called intellectual nugget, the real cream of what the three ideas that you have put in, and what is your own main contribution? After all, research is about something discovering new and reporting something new. If you have just only reported what was already there, then there is no question and the paper will not go through. And most importantly is whatever you have written as a thesis or hypothesis, what is the support, what is the content support, and how you conclude. You cannot suddenly say the data doesn't show, but at the end you kind of make a statement. These kind of things are not usually accepted. So most of the case when a paper is rejected, either your research problem is not properly chosen, problem in the sense experiment, or your results are not up to the mark, your discussion based on the results and hypothesis is not up to the mark. Some very, very, very rarely, they'll also look at maybe how important the topic that we chose. That is, you can see that it is not so important compared to a poor design or results and so on and so forth. Okay, so the most important thing is everybody wants to publish it in big journals, etc., like Nature, which is impact factor of 40 and so on. But it takes time to be able to kind of publish papers in very high impactful journals. But what is the best for us in IEEE is IEEE publishes almost 170 or 80 journals. And more importantly, most of the electrical engineering journals, top, let us say 19 out of 20 journals are actually published by IEEE. IEEE organizes almost about 2,000 conferences annually, and that means that is the biggest opportunity for undergraduate students to be able to write papers and submit in the conferences. And if you are successful, they can get published in what is called, we just now talked about IEEE Explore, which is a repository of IEEE conference papers, etc. IEEE paper review also follow exactly similar procedure like what I kind of mentioned. Depending on who is organizing the conferences, the conference organizers publish IEEE papers to the IEEE Explore, and IEEE Explore has a very rigid set of conference quality committee, which looks at the quality of review, quality of papers, and also whether or not these conference papers fall into the scope of IEEE papers. Okay, you cannot publish anything into an IEEE journals, IEEE conferences. So after they receive these papers, they log into these papers, assigning to various reviewers. Okay, and then they receive the reviews, and again the technical program committee reviews all these reviews that are come out, and then coordinate actual receipt of comments. Sometimes the comments received are such that they have to go back to the authors to correct them, or sometimes if the reviews are very unfavorable, of course, the papers are rejected. Usually about 1/3 of the papers, or sometimes a little better than that, or the number of papers that are accepted, and they are sent to IEEE Explore for possible review and publishing on the IEEE Explore. But they further, as I said, go through the very severe these days review, and then only the entire bunch of papers get published. And of course, you'll feel very happy about it. One point before I want to, and I really want to say that these days, ethics of publications has become a big story, and you all must have heard about the plagiarism, which is in some way of copying somebody else's paper, which is published, either part of it, or knowingly or unknowingly, or fully, or figures, or concepts, without acknowledging, without giving due reference to those papers. This is considered very serious offense, not only by your peers and others, but IEEE now considers it to be really a big crime. In fact, nowadays IEEE publishes set of authors who should be kind of debarred or blocked from submitting papers, etc. So please don't ever try to kind of copy content. For example, even copying content from your own earlier published papers, which are called self-plagiarism, is also something which is not acceptable these days. Doesn't matter what is the small research piece that you have done, what is the new results that have come out, what do you think is something new that you added to the field, it's perfectly fine, but it's never a good idea to kind of look at others and copy them. As I mentioned before, nowadays papers in the assessment of like NIRF, etc., offers almost 30% of weightage for the research publications and research and professional practices. So it's no more papers are only important for some dedicated or motivated researchers, but now it has become very compulsory, very important for on the campuses. And I also want to say for those of you who are research bent of mind, both for students and professionals, there are large number of opportunities where you can do research work with scientists. There is, if you can remember, this is the place, European Science for Nuclear Science, European Center for Nuclear Science called CERN, where it offers facilities by both for academics, professionals, as well as students to work on research projects and publish results. They also organize a lot of, schools, conferences, training programs, summer student programs, and faculty and student programs, and so on, which is very nice because it makes you connect up with the real scientists. And then, you can actually come back to your academic campus and able to kind of work on some of the problems like mentioned. Similarly, the other experiment here, which is in Germany, which also organizes, a lot of student-centric programs. Hundreds of students every year, they're taken as during the, for training programs. Some of the countries have bilateral agreements where the students are exchanged, both undergraduate and master, and of course, PhD students. That's very important. Institutes like TIFR, of course, offer both summer students as well as, so-called research students or PhD students in the fields of physics, chemistry, biology, mathematics, computer science, and science education, and so on. And TIFR also offers what I call the summer students. In fact, right now, I think this particular program is open. Unfortunately, last couple of years due to COVID, we could not open up. But this is a nice opportunity for students to come and work for a couple of months on campus on the real problems. And that if they really like, they can pursue this as their research career. But even if they don't like it, even during this time, they can actually write papers with real scientists working on various fields of their interest. Similarly, TIFR also runs what is called Homi Bhabha Center for Science Education, which works with the college and college students and teachers and engage them into doing something very creative and working on research areas. There are also science academies, maybe you know about this. They also work together and offer almost 500 to 600 fellowships during summer, where the student can choose where they want to work on such research problems. And quite often they end up writing nice papers as a academic, as a student, which is obviously very, very enlightening and very, very important milestone in students' life. Right? There are also international centers where both faculties and students can go and work on varieties of such fields. This one, what is called International Center for Theoretical Physics, is actually located in Italy. They give, if you apply, if you are selected, they'll give entire expenses of airfares, both sides, all the accommodation and everything is taken care. And it's very, very nice programs for young people, especially those who are motivated to do science or mathematics or computer science. Of course, there are a number of organizations, both governmental as well as professional bodies like IEEE, of course, is one of them, who also offer the scholarships and fellowships for the right. I think it is important to kind of take advantage of that. So research at educational institutions obviously is very nice for all the stakeholders. And as I said, institute management plays a big role. And care must be taken to be able to kind of choose the right research areas and topics so that the undergraduate students also become part of the research that goes on the campus. However, every campus must be able to monitor what is the value of, what is the quality of work that happens, especially plagiarism, etc. I think it is good to set up what is called advisory committees, research advisory committees, so that they monitor overall the quality of work that goes on in an institute. So engagement of teachers, faculties, and students within, with the research centers, what I showed you towards the end of my talk, or academic institute for collaborative work. So you can't completely work there forever, right? But if you make a connection and you can come back and then it will be great. You can continue that work in your campus and so on and so forth. And as I told you, there are large number of opportunities for students and faculties to be able to engage with real research fields, and professional bodies like IEEE, etc., will act as catalyst for research ambience on the campus. And I think it's very important that every academic institution kind of respects, or I would say recognize the importance of professional bodies to inculcate research ambience in their campuses. And in a long term, it actually benefits the institute itself. So with that, I would like to thank you very much for your kind attention. And I'll be happy to take any questions if you have.
It's an amazing talk, sir.
Thank you. Thank you.
For a period of 90 minutes.